Thank you. So the aim of this contribution is the description of the mechanical characterization of a commercial tungsten alloy under extreme conditions of temperature, loading, and triaxiality. In fact, these aspects are crucial, and many industrial applications have to consider them. For this reason, a deep knowledge of the mechanical behavior at high strain rates of considered material is required. In general, machinery manufacturing or transport, as well as energy industries, have important dynamic phenomena that are simultaneously affected by extended strain, high strain rate, damage and pressure, as well as elevated temperature gradients. These data were obtained at the Dynamat laboratory, the laboratory founded by me in 2006 in my university in Lugano. That is now one of the laboratories of national relevance recognized by the Swiss Confederation and Swiss National Science Foundation. Dynamat lab is specialized in the studies of dynamic response of material in a large range of strain rate, and it is well equipped with special cutting-edge technologies in this field. Tungsten alloy is a type of cemented carbide in which tungsten carbide particles with extreme hardness are embedded in a matrix metal such as cobalt or nickel. The carbide particles provide a hardness but are in themselves very brittle. However, combined with a ductile metal matrix, outstanding material properties are achieved. Such as high wear resistance, low friction, hardness at a high temperature. The most common application for tungsten alloy is the cutting tool for hardened steels, in which the hard carbide particles provide the cutting surface and through the metal matrix isolate the particles from one to another and prevents the particle-to-particle crack propagations. There is a lack of experimental data on the thermomechanical response of these refractory metals to high strain rate effect at elevated temperature higher than 1000 Celsius degree. The behavior of material under these conditions is of a great interest from the phenomenological point of view. For example, testing the consistency of different constitutive models. Testing was conducted on smooth round specimen of 2 millimeter in diameter and 5 millimeter gauge length. 3 notches configuration were used to evaluate the effects of different triaxiality condition on stress strain and keeping constant the net cross section of 2 millimeter in diameter. The quasi-static tests were carried out by means of an electromechanical universal machine, highlighting the elastoplastic and brittle behavior of this alloy. The dynamic response of this commercial tungsten alloy at high strain rate was investigated by using a split Hopkinson tensile bar installed in our laboratory, as shown in this slide. It consists of 2 straight circular bar with a diameter of 10 millimeter and the length of 9 and 6 meter. The first 6 meter of the longer bar is used as a pretensioned bar, while the rest 3 meter is used as input bar. The second bar serves as an output bar. The tungsten alloy specimen is screwed normally into the input and output bars. By means of a hydraulic jack placed at the end of the bar, and thanks to the blocking device, it's possible the pretension bar is pulled, so we can store elastic energy and regulate the velocity in relation to the load amplitude. So we obtain the signals the very clean signals in terms of incident, reflect, and transmitted pulse, and the constancy of the incident pulse. The test we have carried out at a high strain rate at room temperature and elevated temperature. And the last one, thanks to the induction heating system, that we are able to heat up the sample to elevated temperature and obtaining a picture like this one. In this slide, I've resumed the results at a strain rate at room temperature on smooth samples. The strain rate effects on mechanical properties of this tungsten alloy can be observed in the table shown in the slide. By depicting the engineering stress versus engineering strain, it's possible to highlight the mechanical properties. And 3 targets of high strain rate were set as 850 strain per second and 422 strain per second, obtaining by imposing respectively at room temperature 26, 35, and 50 kilonewton in the preloading bar. In fact, it's possible to observe a significant increase of the strength and strain capacity. One of the main challenges in studying the influence of a high temperature on tungsten alloy under high strain rate is the lack of experimental data. And this is because it's very difficult to generate the necessary high strain rate loading in high elevated temperature. And this is why the preliminary study has been conducted. Keeping the same loading conditions, we have observed a general increase of the evaluated strain rate with increasing temperature. You can see the testing temperature use the same input signals. The input signals, so it's not affected by temperature, but the reflection waves are. With increasing temperature, the effective strain rate is expected to increase linearly. Now, at room temperature, with the constancy of 850 strain per second, we increase the temperature and we obtain these results using the same preloading conditions and the temperature varying from ambient temperature up to 1100 Celsius degree. And it can be noted that the strength of this commercial tungsten decreases with increasing temperature under strain rate loading conditions, and then fracture strain is increased in the same interval. The stress triaxiality at the center of the net section can be calculated by the formula proposed by Bridgman. And the material parameters of the Johnson-Cook damage model were obtained by using the experimental data. And according to this parameter, we have created the failure surface shown in this slide. On the right for 20 Celsius degree, and on the left for the 20 Celsius degree, 1100 for the right one. As a conclusion, this preliminary investigation on mechanical response of this commercial tungsten alloy was performed to analyze the effect at different temperatures strain rate triaxiality. A methodology for testing materials at a high strain rate was presented. The methodology consists of performing dynamic test in tension using the split Hopkinson tensile bar and heating the specimen using the induction coil system. The heating system is properly designed to concentrate the heat flux in the gauge length of the specimen. And the investigated range in the temperature was from temperature for ambient temperature up to 1100. So the next step will be addressed to eliminate the problems of oxidation of these alloys, creating a vacuum protection and an improvement of the setup allows the fast video recording the test, creating the post failure phenomena. I'd like to thank our sponsor, Arma Swiss, and all of us for the kind attention. Thank you.